Imagine standing on Earth, looking up at the night sky, and knowing that the nearest star beyond our sun is so far away that even traveling at the speed of light, it would take over 4 years to reach it. 4 years of traveling at 186,000 miles per second. Think about that for a moment. At the fastest speed anything in the universe can move, according to our current understanding of physics, you would still need more than 4 years to reach our closest stellar neighbor, Proxima Centauri. Now consider this. Our galaxy, the Milky Way, spans about 100,000 light-years across. The Andromeda Galaxy, our nearest major galactic neighbor, sits 2.5 million light-years away. And the observable universe. It stretches 93 billion light-years in diameter. The distances are so vast, so incomprehensibly enormous, that they seem to mock humanity's deepest dreams of exploration. We are trapped, it seems, by the very fabric of reality itself. Or are we? What if there was a way to break free from these cosmic shackles? What if the universe had left us a loophole, a backdoor in the laws of physics that could allow us to traverse these impossible distances not in millions of years, but in days, hours, or even minutes? This is the tantalizing promise of warp drive technology, a concept that straddles the razor's edge between science fiction and scientific possibility. It's an idea that has captivated physicists, engineers, dreamers, and storytellers for generations. But here's what makes this subject so absolutely fascinating. Unlike so many other fantastical technologies imagined in fiction, warp drive might actually be possible. Not guaranteed, not proven, but possible within the known laws of physics. And that changes everything. The year was 1994 when a Mexican theoretical physicist named Miguel Alcubierre published a paper that would send shockwaves through the scientific community. Working at the University of Wales, Alcubierre proposed something extraordinary. A mathematical model that showed how a spacecraft could theoretically travel faster than light without actually violating Einstein's theory of relativity. Let that sink in for a moment. Here was a serious scientist, working within the framework of general relativity, the same theory that seems to impose an absolute cosmic speed limit, showing that faster-than-light travel might not be forbidden after all. The paper, titled "The Warp Drive: Hyperfast Travel Within General Relativity," was published in the journal Classical and Quantum Gravity, and it represented something revolutionary. Not a technological breakthrough, but something perhaps even more important. Proof that the universe might allow for what we had long dreamed of. But before we dive deeper into Alcubierre's remarkable discovery and what it means for humanity's future among the stars, we need to understand why faster-than-light travel seems impossible in the first place. We need to go back to 1905, to a 26-year-old patent clerk in Bern, Switzerland, who was about to overturn our entire understanding of space, time, and reality itself. His name, of course, was Albert Einstein, and his special theory of relativity would reveal that the universe operates in ways far stranger than anyone had imagined. Einstein's special relativity rests on a foundation that seems simple but has profound implications. The speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. Always 299,792,458 meters per second. Always the same. This might not sound particularly revolutionary until you work through the consequences. What Einstein realized was that space and time are not separate, independent entities. They're woven together into a four-dimensional fabric called space-time. And as you move faster through space, something extraordinary happens. Time slows down for you relative to observers who are moving more slowly. This isn't science fiction. This is measured, verified, experimental fact. Atomic clocks flown on airplanes run slightly slower than identical clocks on the ground. GPS satellites have to account for relativistic time dilation, or they would quickly become useless. Particles accelerated to near light speeds in particle accelerators live longer than their stationary counterparts because time literally passes more slowly for them. The faster you go, the more extreme the effect becomes. At 90% the speed of light, time passes at about 44% of normal rate. At 99% light speed, it's down to about 14%. At 99.9% light speed, you're at roughly 4.5% of normal time flow. But here's where it gets truly mind-bending, truly limiting. As you approach the speed of light, your mass effectively increases. Not your rest mass, but your relativistic mass, the resistance to acceleration. It takes more and more energy to make you go faster. And at the speed of light itself, your mass becomes infinite. The energy required to accelerate you to light speed becomes infinite. This is the cosmic speed limit, the ultimate barrier, written into the very structure of reality. Nothing with mass can reach the speed of light, let alone exceed it. This is why physicists have long said that faster-than-light travel is impossible. Not just technologically challenging, but fundamentally impossible according to the laws of physics. Think about what this means for space exploration. The Apollo astronauts, traveling to the moon at about 25,000 miles per hour, covered roughly 240,000 miles in 3 days. That's impressive by human standards, but it's only about 0.0037% the speed of light. The Voyager 1 spacecraft, now the most distant human-made object, traveling at about 38,000 miles per hour relative to the Sun, has been journeying for over 45 years and has only just barely entered interstellar space. It would take Voyager over 70,000 years to reach Proxima Centauri if it were headed in that direction, which it isn't. Even our fastest spacecraft are glacially, impossibly slow on cosmic scales. The fastest speed that current physics and engineering suggests might be achievable is perhaps 10 to 20% the speed of light, and that would require revolutionary new propulsion technologies we don't yet possess. Nuclear pulse propulsion, fusion rockets, antimatter drives, laser-pushed light sails. These are concepts that could, theoretically, get us to a significant fraction of light speed. But even at 20% light speed, reaching Proxima Centauri would take over 20 years. Reaching interesting destinations across the galaxy would take centuries or millennia. Generation ships, where multiple generations live and die during the journey. Cryogenic suspension, freezing travelers for the duration. These are the solutions proposed for interstellar travel within the bounds of conventional physics, and they're deeply unsatisfying. They're barriers that seem to confine humanity to a tiny corner of space, able to know intellectually that wonders exist beyond our reach, but forever unable to touch them. Can you imagine what that feels like to consider? The cruel irony of gaining the knowledge of what's out there while being denied the ability to reach it? Knowing that countless worlds orbit distant stars, that the universe is filled with mysteries and wonders, but that the cosmic speed limit makes them effectively unreachable within any human timescale? This is the existential frustration that drives the search for faster-than-light travel. Not just curiosity, but a deep, almost desperate need to break free from our cosmic prison. And this is precisely where Miguel Alcubierre's 1994 paper becomes so important, so revolutionary. Because what Alcubierre realized was that while Einstein's relativity forbids objects from moving through space faster than light, it says nothing about the motion of space itself. Let me explain what that means, because this distinction is absolutely crucial, and it's the key to understanding how warp drive could theoretically work. General Relativity, Einstein's 1915 expansion of his special theory, describes gravity not as a force but as the curvature of space-time caused by mass and energy. Massive objects like stars and planets bend the fabric of space-time around them, and objects moving through this curved space-time follow paths we perceive as orbits. But here's the critical point. Space-time itself is dynamic. It can stretch, compress, expand, and contract. And there's no law that says space-time itself can't move faster than light. In fact, we have direct evidence that it does. The universe itself is expanding, and distant galaxies are receding from us at speeds that exceed the speed of light. Not because they're moving through space faster than light, but because the space between us and them is expanding. A galaxy 10 billion light-years away is receding from us at more than twice the speed of light because of cosmic expansion. This doesn't violate relativity because the galaxy isn't moving through space that fast. The space itself is stretching. The distinction is subtle but absolutely fundamental. Alcubierre's brilliant insight was to ask, if space can naturally expand and contract, could we artificially manipulate space-time to create a region that contracts in front of a spacecraft and expands behind it? Imagine space-time as a rubber sheet. Normally, a spacecraft would have to crawl across this sheet, limited by how fast it can move through the rubber. But what if, instead of moving through the rubber, you could grab the rubber ahead of you and pull it toward you while pushing the rubber behind you away? You wouldn't be moving through space faster than light. The spacecraft would actually be stationary relative to the space immediately around it, existing in a bubble of flat spacetime. But that bubble itself would be moving through space faster than light, carried along by the contraction of space in front and expansion behind. This is the Alcubierre warp drive. The mathematics are complex, but the concept can be visualized. Picture a surfer on a wave. The surfer isn't moving through the water faster than is physically possible for a human to swim. Instead, the surfer is riding on the wave itself, and the wave carries them forward at speeds far exceeding what they could achieve swimming alone. The Alcubierre drive would create a wave in spacetime, a bubble that carries the spacecraft along with it. Inside this bubble, known as a warp bubble, space would be flat and normal. Time would pass normally. There would be no relativistic effects, no time dilation, no mass increase. You could have gravity, walk around, live normally. But outside the bubble, space-time would be severely warped, contracted in front, expanded behind, propelling the entire bubble forward at any speed you could generate, even many times the speed of light. When Alcubierre published this paper, the reaction in the physics community was mixed but intense. On one hand, respected physicists confirmed that yes, mathematically, his solution was consistent with general relativity. He hadn't made an error. The equations worked. This was a legitimate solution to Einstein's field equations. On the other hand, there were immediate and serious concerns about whether such a thing could actually be built, and those concerns remain central to the debate today, nearly 3 decades later. The first and most daunting problem is energy. When physicists analyzed Alcubierre's original model, calculating how much energy would be required to create and maintain a warp bubble, the numbers were horrifying. The estimates suggested you would need an amount of energy equivalent to the total mass energy of a significant portion of the observable universe. Some calculations put it at the mass energy equivalent of the planet Jupiter. Others suggested even more. This is energy on a scale so vast that it makes thermonuclear weapons look like firecrackers. It's energy that our civilization, even in our wildest future projections, seems utterly incapable of generating or controlling. But there's a second problem, even more exotic and perhaps more troubling. The energy required isn't just enormous in quantity, it's exotic in nature. To create the space-time geometry that Alcubierre's equations describe, you need something called negative energy density, or equivalently, exotic matter with negative mass. Now, this is where we need to be very careful and very precise about what we mean, because negative energy sounds like pure science fiction, but it's actually something that exists in quantum physics under very specific circumstances. Have you ever heard of the Casimir effect? Discovered in 1948 by Dutch physicist Hendrik Casimir, it's a quantum phenomenon where two uncharged, parallel metal plates placed very close together in a vacuum will experience an attractive force pushing them together. This happens because the vacuum isn't truly empty. According to quantum field theory, even empty space seethes with virtual particles, pairs of particles and antiparticles that pop into existence and annihilate each other almost instantly. These quantum fluctuations create a sort of baseline energy in the vacuum, called vacuum energy or zero-point energy. When you place two plates very close together, you restrict the wavelengths of virtual particles that can exist between the plates compared to the space outside them. This creates a difference in vacuum energy, a pressure differential, and the plates are pushed together. The region between the plates has less vacuum energy than the surrounding space, which means it effectively has negative energy density relative to the normal vacuum. The Casimir effect has been experimentally verified many times. It's real. Negative energy density, in this very specific quantum mechanical context, exists. And this has led some physicists to speculate that perhaps, just perhaps, the exotic matter or negative energy required for a warp drive isn't completely impossible. Maybe, using extremely advanced technology and our understanding of quantum field theory, we could generate the negative energy density needed to create an Alcubierre warp bubble. But here's the problem. The Casimir effect generates negative energy on an absolutely minuscule scale. The forces involved are tiny. We're talking about energies measured in fractions of a nanojoule. The amount of negative energy you'd need for a warp drive is monumentally larger, and it's not at all clear that quantum effects could be scaled up to macroscopic levels. It might be fundamentally impossible to generate large quantities of negative energy. The physics might simply not allow it. There's also a question of stability. Even if you could somehow generate the required negative energy and create a warp bubble, would it be stable? Or would quantum effects cause it to collapse almost instantly? Some theoretical studies suggest that warp bubbles might be inherently unstable, that tiny quantum fluctuations would cause them to fall apart before they could be useful. Others suggest that maintaining the bubble would require constant, precise adjustment of the energy distribution, a level of control that might be technologically impossible. And then there are the causality problems. Causality is the principle that cause precedes effect, that events happen in a logical sequence. Faster-than-light travel, even through warp drive, potentially allows for violations of causality. In special relativity, observers moving at different speeds disagree about the order of events. If you can travel faster than light, even by warping space, you might be able to construct scenarios where you arrive at a destination before you left, creating time travel paradoxes. You could potentially send information into your own past, creating logical contradictions. Most physicists believe that the laws of physics must somehow prevent these paradoxes, but it's not entirely clear how this protection would work with warp drives. Some propose that quantum effects or unknown aspects of physics would prevent paradoxes, that the universe has built-in safeguards against causality violations. But this remains speculative. Despite all these enormous challenges, research into warp drives didn't stop with Alcubierre's paper. In fact, it accelerated. Throughout the late 1990s and into the 2000s, physicists continued to explore the concept, refining the mathematics, looking for ways to reduce the energy requirements or to find alternative geometries that might be more achievable. In 1999, physicist Chris van den Broek published a significant paper proposing a modification to the Alcubierre metric. Van den Broek showed that the volume of the warp bubble could be made much smaller from an external perspective while maintaining a larger interior volume, somewhat like the TARDIS from Doctor Who, bigger on the inside than the outside. This modification dramatically reduced the energy requirements, bringing them down from Jupiter mass scales to perhaps something closer to the mass of the Sun, or in some optimistic calculations, even less. Still an enormous, civilization-straining amount of energy, but at least within the realm of what an extremely advanced civilization might theoretically achieve. Then, in 2012, Harold "Sonny" White, a physicist at NASA's Johnson Space Center, made headlines around the world when he announced that he had been investigating warp drive technology and had found ways to potentially reduce the energy requirements even further. White was working at NASA's Advanced Propulsion Physics Laboratory, sometimes called EagleWorks, specifically tasked with investigating breakthrough propulsion concepts. His analysis suggested that by optimizing the shape and thickness of the warp bubble, making it more like a rounded rugby ball than a sphere, the energy requirements could be reduced to perhaps the mass energy equivalent of a small spacecraft, maybe around 700 kilograms. Think about that reduction. From the mass energy of Jupiter to the mass of the Sun to potentially less than a ton. If true, this would put warp drive technology within the realm of theoretical possibility for a sufficiently advanced civilization. Not easy, not anywhere close to our current capabilities, but not requiring godlike powers over the universe either. White's announcements generated enormous excitement in the media and the public. NASA, the actual NASA, was researching warp drives. The dream of Star Trek might be real after all. But we need to be careful and honest here about what White's work actually represented. He was doing theoretical calculations, mathematical modeling. He wasn't building a warp drive. He wasn't even close to building a warp drive. He set up experiments to look for tiny perturbations in spacetime using an extremely sensitive interferometer, hoping to detect microscopic warp effects. The experiments were looking for effects orders of magnitude smaller than what would be needed for actual propulsion, essentially trying to determine if the physics allowed for any warping of spacetime at all using electromagnetic fields. And the results of these experiments have been ambiguous at best. No clear warp effect has been detected. Other physicists have raised concerns about White's energy calculations, suggesting that his optimistic estimates might have underestimated the true requirements. Furthermore, even White's reduced energy estimate still requires exotic matter with negative energy density. That fundamental problem remains. The shape optimization reduces the amount of exotic matter needed, but it doesn't eliminate the requirement. And we still have no confirmed way to generate macroscopic amounts of negative energy. In 2021, another development sparked renewed interest. Physicist Eric Lentz, working at the University of Göttingen in Germany, published a paper proposing a new class of warp drive solutions that, remarkably, don't require negative energy at all. Lentz's approach uses configurations of positive energy, arranged in specific soliton shapes that create regions where space contracts in front and expands behind. Solitons are wave-like structures that maintain their shape as they propagate, and they appear in various physical systems. Lentz showed mathematically that soliton-based warp drives could theoretically achieve faster-than-light travel without exotic matter. This sounds almost too good to be true, and the catch is that the energy requirements for Lentz's positive energy warp drives are astronomical. We're talking about energy equivalents of entire stars, possibly hundreds of times the mass of the Sun. These are energies that make even Alcubierre's original estimates look modest. For a civilization like ours, they're completely unattainable. But Lentz's work is significant because it suggests that warp drives might not be fundamentally impossible due to the need for negative energy. If we can find ways to reduce the energy requirements of positive energy warp drives, or if a sufficiently advanced civilization could harness stellar-scale energies, then warp drive technology might be achievable without requiring the exotic matter that we don't know how to produce. More recently, in 2021, DARPA, the Defense Advanced Research Projects Agency of the United States Department of Defense, announced funding for research into warp drives and other faster-than-light concepts as part of a program exploring breakthrough physics. This doesn't mean DARPA thinks warp drives are imminent or even necessarily possible, but it indicates that serious government research organizations consider the physics worthy of investigation. When military research organizations start funding something, it suggests that the concept has moved from pure fantasy into the realm of at least distant possibility. Let's pause here and ask ourselves some critical questions. Questions you should genuinely consider. If warp drive technology were proven to be fundamentally impossible, how would that change your view of humanity's future? Would we accept being forever confined to our tiny region of space, able to explore perhaps a handful of nearby stars over centuries, but never able to traverse the galaxy? Or would we find meaning in other pursuits, perhaps virtual realities, perhaps enhanced longevity, perhaps uploading consciousness into machines that could endure the long centuries of slower-than-light travel? And conversely, if warp drives are possible but require energy scales or technologies we can't imagine achieving for thousands or millions of years, does that possibility matter to us now? Is hope alone valuable, even if fulfillment is unimaginably distant? To understand why these questions matter so much, why the possibility of warp drives captivates us so deeply, we need to explore what faster-than-light travel would actually mean for civilization. Not just as a technological achievement, but as a transformation of human existence and our place in the cosmos. Imagine for a moment that someone solves the engineering challenges. Imagine that in the year 2150, or 2300, or whenever, humanity develops a working warp drive. Not a perfect one, perhaps. Maybe it can only achieve a maximum speed of 10 times the speed of light, or 100 times. What does the galaxy look like at those speeds? At 10 times light speed, Proxima Centauri is 5 months away. The center of our galaxy, 25,000 light-years distant, becomes a 2,500-year journey. Still enormously long, but comparable to historical human civilizations. At 100 times light speed, destinations across hundreds of light-years become reachable within a human lifetime. The nearest 1,000 star systems, encompassing tens of thousands of potentially habitable worlds based on current exoplanet statistics, become accessible to direct exploration and even colonization. At 1,000 times light speed, much of the galaxy opens up. A journey across the 100,000 light-year diameter of the Milky Way would take a century, long but manageable with either cryogenic suspension or generation ship concepts. The implications are staggering. Humanity would transform from a single planet species to a true galactic civilization. We could search for life on other worlds not by analyzing distant spectra but by going there and looking. We could establish colonies on exoplanets, creating new branches of human civilization adapted to different worlds. The genetic and cultural diversity of our species would explode as populations separated by dozens or hundreds of light years evolved independently. Earth would become one world among thousands, the origin point of humanity but no longer the sole repository of our species. Resources would become effectively infinite. Asteroids rich in platinum, rare earths, and other valuable materials orbit countless stars. Entire solar systems could be industrialized. The energy of stars could be harnessed using megastructures like Dyson spheres or Dyson swarms. The material limits that constrain our civilization on Earth, the competition for finite resources, the zero-sum thinking that drives so much conflict, could potentially fade as the abundance of the galaxy becomes accessible. Knowledge would advance at unprecedented rates. Imagine studying stellar evolution not through telescopes but by visiting stars at different life stages. Imagine comparative planetology across thousands of worlds. Imagine searching for alien civilizations not by hoping to detect their radio signals across light years but by systematically exploring candidate systems. Even if life is rare, if only 1 in a million star systems harbors life, the Milky Way with its 200 to 400 billion stars would still host hundreds of thousands of living worlds. With warp drives, finding them becomes a matter of time and effort rather than impossibility. But there would be dark implications too. Consider the political and social ramifications. Earth's nations and power structures are built on geography, resources, and the ability to project power across distances. When travel times between stars are measured in weeks or months instead of decades or centuries, what happens to governance? Could Earth maintain authority over colonies dozens of light years away, or would those colonies inevitably become independent, potentially hostile powers? History shows that colonies often rebel against distant homelands. The American Revolution, the independence movements across the former European colonial empires, all were enabled partly by the difficulty of projecting power across oceanic distances. Interstellar distances, even with warp drives, would be far greater. There's also the potential for conflict and war on a horrifying scale. If warp drives are possible, then warships with warp drives are possible. Weapons delivered at faster-than-light speeds could devastate planets with little to no warning. An enemy fleet could appear in a star system without any possibility of early detection by light-speed sensors. The strategic calculus of war would transform entirely. Perhaps worse, the sheer distances involved might make atrocities easier to commit. When a world is years or decades away even at FTL speeds, when communication lags prevent any real-time oversight, what prevents colonizers or corporations or military forces from committing genocides or ecological devastations far from any accountability? And then there are the questions about what we might encounter out there. The Fermi paradox asks, if the universe is so vast and old, where are all the aliens? If intelligent life is at all common, we should see evidence everywhere. The galaxy is old enough that even at slower-than-light speeds, a single expansionist civilization could have colonized the entire Milky Way many times over by now. Yet we see no signs of galactic empires, no Dyson spheres blocking out distant stars, No massive engineering projects, no visiting probes, no radio signals. The silence is profound and disturbing. There are many proposed solutions to the Fermi paradox. Perhaps life is incredibly rare. Perhaps intelligence is rare. Perhaps civilizations inevitably destroy themselves before achieving interstellar travel. Perhaps they deliberately hide from us. Perhaps they're here and we don't recognize them. But one particularly unsettling possibility is that interstellar travel, even with warp drives or other FTL methods, is harder or more dangerous than we imagine. Perhaps there's something out there, some hazard or predator or natural phenomenon, that makes interstellar travel fatal. Perhaps civilizations that develop warp drives discover too late that using them attracts unwanted attention or triggers some cosmic disaster. This is pure speculation, of course, but it's speculation grounded in the genuine mystery of why the universe seems so empty when it should be teeming with life and activity. What if the development of warp drive is the great filter, the hypothetical barrier that prevents civilizations from becoming widespread and long-lived? What if there's something about manipulating space-time on the scales required for warp bubbles that's inherently catastrophic, and every civilization that tries it destroys itself or draws the attention of something that destroys them? These are dark thoughts, but when contemplating technologies that manipulate the fundamental structure of reality, perhaps caution is warranted. Let's return to the science and explore some of the more technical challenges and discoveries that researchers have uncovered. One of the most significant concerns about warp drives involves what happens at the boundary of the warp bubble, the edge where normal spacetime transitions into the severely warped region. This boundary, sometimes called the warp bubble wall, is a region of extreme spacetime curvature, and the physics there becomes very strange. Some studies have suggested that particles and radiation encountering the front of a moving warp bubble would be blue-shifted to enormous energies and possibly accumulated. As the warp bubble travels, it sweeps up stray particles, atoms of interstellar gas, cosmic ray particles, even photons. These particles interact with the warp bubble in complex ways. Some calculations suggest they could be trapped at the front edge of the bubble, accumulating over the journey. Then, when the warp bubble collapses and the ship decelerates, all of this accumulated energy and matter could be released in a catastrophic forward-directed burst. Physicist William Hiskog pointed out in the 1990s that the energy released from a decelerating warp bubble could potentially devastate anything in front of the ship, including the destination you're traveling to. Imagine accelerating to 1,000 times light speed, traveling across hundreds of light years, accumulating high-energy particles all the way, and then arriving at your destination star system only to inadvertently sterilize it with a blast of radiation when you decelerate. This would be an unintended consequence of monumental proportions, making warp drives not just useless but actively dangerous. Other physicists have argued that quantum effects might prevent this accumulation, that particles would tunnel through or around the warp bubble rather than accumulating. The truth is we don't know. Without being able to create even a tiny warp bubble experimentally, we can't test how matter and radiation actually interact with warped spacetime at these extremes. The mathematics gives different answers depending on the assumptions and approximations used. There's also the question of navigation and control. Inside a warp bubble, you're surrounded by severely warped spacetime. The light from stars outside would be distorted, possibly completely blocked. You might not be able to see where you're going at all. And since you're not actually moving through space locally, you can't steer by firing rockets. The direction of travel is determined by the asymmetry of the spacetime warping around you. How would you control that? How would you navigate to a precise destination light years away when you can't see outside and can't make course corrections the way we do with conventional spacecraft? Some proposals suggest you would need to chart your course in advance, create the warp bubble with the appropriate directional asymmetry, and then hope you got it right. The warp bubble would carry you to the destination, and only when you collapse the bubble would you find out where you actually are. If you miscalculated even slightly, an error of a fraction of a degree over hundreds of light years could leave you light years from your target, stranded in interstellar space. Other ideas propose using advanced sensors that could somehow peer through or around the warp bubble, perhaps using gravitational wave detectors or quantum effects, but these remain entirely speculative. And what about creating and collapsing the warp bubble itself? Alcubierre's original conception and most subsequent models describe the warp bubble as existing in a steady state, already formed around the ship. But realistically, you need to be able to turn it on and off. You need to start from normal space-time, initiate the warp bubble, travel, and then collapse it. The dynamics of this process are poorly understood. Some studies suggest that creating a warp bubble from inside it might be impossible, that you would need external infrastructure to generate the exotic matter distribution or energy configuration. This could mean you need massive installations at your departure point and destination, like warp gates or launchers. You couldn't just point a warp-capable ship at a star and go. You'd need to build infrastructure there first, which you could only do at slower-than-light speeds. This creates a chicken-and-egg problem. To explore new star systems with warp drive, you need infrastructure at those systems, but to build that infrastructure, you need to get there without warp drive. Some futurists propose that the first era of interstellar expansion would use slow, sublight colony ships that take centuries to reach nearby stars. These colonies would then build warp infrastructure, allowing faster ships to follow. Over time, a network of warp-connected systems would grow, but it would take a long time to establish. Alternatively, if warp bubbles can be created and collapsed from within, you might not need fixed infrastructure, but then you face different challenges. The energy to create the warp bubble has to come from somewhere, probably stored on the ship itself. We're talking about energies that, even in the most optimistic scenarios, are enormous. How do you store that much energy in a spacecraft? Antimatter has the highest energy density of any known form of matter, releasing energy equivalent to its entire mass when it annihilates with normal matter. But even antimatter storage on the required scale seems fantastically difficult and dangerous. A malfunction in the containment of tons of antimatter would be catastrophic. Doesn't even begin to cover it. You might wonder, has anyone proposed alternative forms of faster-than-light travel that don't have these problems? The answer is yes, several, and they each have their own challenges. Wormholes, for instance, are another solution to Einstein's equations that allow for faster-than-light travel, or more precisely, they allow for shortcuts through space-time. Instead of warping space to move you faster than light, a wormhole connects two distant points in space through a tunnel, a throat through a higher dimension. Travel through the wormhole might be at slower-than-light speeds, but you reach your destination much faster than light would traveling through normal space because you've taken a shortcut. Wormholes also appear to require exotic matter with negative energy to hold them open and make them traversable. Without exotic matter, the solutions to Einstein's equations that describe wormholes suggest they would collapse instantly or have throats so small and so violent that nothing could pass through them. Kip Thorne and Michael Morris explored traversable wormholes in detail in the 1980s and concluded that while they might be allowed by the laws of physics, creating and maintaining them would require the same kind of exotic matter that we don't know how to produce. There's also the concept of the Einstein-Rosen bridge, sometimes called a Schwarzschild wormhole, which is a non-traversable wormhole that connects the inside of a black hole to a white hole. These appear naturally in the mathematics of black holes, but they're unstable. They pinch off before anything can cross through them, and even if you could traverse one, you'd probably be destroyed by tidal forces and radiation. Not exactly a practical transportation system. Another idea is quantum teleportation, but we need to be very clear about what this means. Quantum teleportation, which has been experimentally demonstrated with photons and atoms, doesn't actually teleport matter or energy. It teleports quantum states, the information describing a quantum system. You need a classical communication channel to complete the process, and that's limited to light speed. So quantum teleportation can't be used for faster-than-light communication or travel. It's useful for quantum computing and quantum cryptography, but it doesn't get around the cosmic speed limit. Some more exotic ideas involve manipulating dimensions. String theory and some other models of fundamental physics suggest there might be additional spatial dimensions beyond the three we experience. These extra dimensions are theorized to be compactified, curled up on incredibly small scales. But some speculation suggests that if we could access these extra dimensions, we might travel through them, taking shortcuts through higher dimensional space to reach distant points in our three-dimensional universe faster than light could through normal space. This is highly speculative and far beyond our current understanding or technology. We don't even know if extra dimensions exist, let alone how to access or navigate through them. There's a concept in science fiction and some speculative physics called hyperspace, a separate realm of existence where the laws of physics are different, allowing faster-than-light travel. Ships enter hyperspace, travel faster than light there, and then exit back into normal space at their destination. There's no established scientific basis for hyperspace, no equations in general relativity or quantum field theory that predict such a thing, but it can't be ruled out entirely. Our understanding of physics is incomplete. We know that quantum mechanics and general relativity, our two best theories, are incompatible in extreme conditions. The unification of these theories, a theory of quantum gravity, might reveal new structures or dimensions of reality. Could one of those be a hyperspace-like domain? It's possible, but purely speculative at this point. Now, let's consider what theoretical physicists and cosmologists think about all this. The community is divided, which is actually healthy for science. Some physicists, probably the majority, are deeply skeptical that faster-than-light travel will ever be practical, even if it's not absolutely forbidden by the laws of physics. The engineering challenges are so extreme, the energy requirements so vast, the need for exotic matter so problematic, that they consider it effectively impossible for any foreseeable civilization. But there's a minority of physicists who take warp drives and other FTL concepts seriously as long-term possibilities. They argue that dismissing ideas because they're technologically difficult is short-sighted. After all, there are many examples in history where things deemed impossible became routine. Heavier-than-air flight was considered impossible by many scientists even shortly before the Wright brothers achieved it. Nuclear energy was considered impossible until the underlying physics was understood. Reaching the moon was fantasy until it was accomplished. The counterargument is that those achievements didn't require violating or circumventing fundamental laws of physics. They required engineering within the known laws. Warp drives, even if they don't technically violate relativity, require manipulating space-time and generating exotic matter in ways that might be fundamentally impossible, not just hard. Perhaps the most honest assessment is this: warp drives remain in the category of things that are not forbidden by the laws of physics as we currently understand them, but that face such enormous practical obstacles that we cannot say whether they will ever be achievable. They exist in a strange liminal space between science fiction and science fact, not definitively in either category. And that uncertainty, that possibility, is what keeps researchers investigating and dreamers dreaming. Because the stakes are so high. The difference between a universe where FTL travel is possible and one where it isn't is the difference between humanity remaining forever confined to a tiny bubble around one star and humanity spreading across the galaxy. It's the difference between maybe, if we're very lucky, colonizing a handful of nearby systems over thousands of years, and establishing a true interstellar civilization encompassing thousands of worlds. It's the difference between probably never encountering alien life directly and being able to search the galaxy systematically. The magnitude of the difference is hard to overstate. Let's think about the cultural impact of warp drive concepts. Star Trek, which popularized the term warp drive, imagined a future where faster-than-light travel was routine, where Starfleet vessels could reach distant stars in days or weeks, enabling exploration and diplomacy across the galaxy. The show's optimistic vision of humanity united in peaceful exploration, encountering diverse alien species and growing through those encounters, has inspired generations. Many scientists and engineers working today cite Star Trek as the reason they entered their fields. But Star Trek glossed over the difficulties. In the show's lore, the warp drive was invented by Zefram Cochrane in 2063 after World War III, using materials scavenged from a nuclear missile. It worked by generating a warp field through matter-antimatter reactions, creating a subspace bubble. The specifics were intentionally vague because Star Trek is entertainment, not a physics lecture. But that vagueness may have given people an overly optimistic sense of how achievable warp drives might be. Other science fiction has treated faster-than-light travel differently. The Expanse, a more recent and more scientifically rigorous series, confines itself to the solar system and doesn't use FTL travel, showing what realistic near-future space exploration might look like. Interstellar, the Christopher Nolan film, uses wormholes for interstellar travel and consulted physicist Kip Thorne to keep the science as accurate as possible within the story's framework. The depiction of the wormhole and the black hole gargantua were based on actual physics simulations. The variety of approaches in fiction reflects the uncertainty in the science. Nobody knows for sure, so storytellers can explore different possibilities. But this also means that public understanding is muddled. Many people think warp drives are either definitely possible or definitely impossible, when the truth is we genuinely don't know. There's also a philosophical dimension to consider. Why do we want faster-than-light travel so badly? Is it just pragmatism, the desire to explore and colonize? Or is it something deeper, something about our nature as humans? We are a restless species. For tens of thousands of years, we've migrated, explored, pushed into new frontiers. We crossed oceans in fragile boats, traversed deserts and ice sheets, climbed mountains, dove into ocean depths. When we reached the moon, it wasn't because of immediate practical benefit, but because it represented a frontier, a challenge, a destination beyond where we'd been. The stars are the ultimate frontier. They represent the unknown, the unreachable made potentially reachable. The desire to go there is, in a sense, a desire to transcend our limitations, to prove that we're not bound by the circumstances of our origin. It's a desire for meaning in a vast universe that can seem indifferent to our existence. If we can reach the stars, if we can make the galaxy our home, then perhaps we matter, perhaps our existence has significance on a cosmic scale. But there's a darker aspect too. Perhaps the desire for FTL travel is a desire to escape. Escape from Earth's environmental problems, resource limitations, political conflicts. The fantasy that we can leave behind our mistakes and start fresh on new worlds. This fantasy is problematic because it suggests we don't need to fix our problems here. We can just move on. But in reality, even with warp drives, Earth would remain home to billions of people for a long time. We can't just abandon it. And the problems we have here, the tendencies toward conflict, exploitation, environmental destruction, those aren't problems of place. They're problems of human nature and social structure, and we'd carry them with us to the stars. So perhaps the quest for warp drive technology should be coupled with a quest to improve ourselves, to create social, political, and economic systems that are wise and sustainable, that we'd actually want to spread to other worlds. Otherwise, we might just be spreading our dysfunctions across the galaxy, creating new opportunities for suffering and destruction on an interstellar scale. Let's explore some of the more recent theoretical developments in warp drive research, because the field hasn't been static. In 2020, physicist Alexei Bobrick and co-author Johnny Martiri published a paper analyzing a general class of warp drive spacetimes. They classified warp drives into physical and non-physical categories based on whether they respect certain energy conditions, mathematical constraints that physicists believe should be satisfied by realistic matter and energy. Their conclusion was that physical warp drives, ones that don't require negative energy, can exist but are subliminal. They can't exceed the speed of light. Superluminal warp drives, ones that go faster than light, appear to require violations of the energy conditions, meaning they need exotic matter. This is a somewhat pessimistic conclusion because it suggests that you can't have your cake and eat it too. Either you have a warp drive that doesn't need exotic matter but can't go faster than light, making it not much better than other advanced propulsion systems, or you have a faster-than-light warp drive that requires exotic matter we can't produce. However, Bobrick and Martiri's analysis also provides a rigorous framework for thinking about warp drives, moving the discussion from isolated models to a general theory. In early 2021, The announcement of Eric Lentz's positive energy warp drive solution generated excitement because it seemed to contradict this conclusion. But as noted earlier, Lentz's solution requires such vast amounts of energy that it's practical only for extremely advanced civilizations, if at all. The energy requirements are so high that they might as well be impossible for us. Then, in late 2021, a team including physicist Harold White published a paper describing the accidental discovery of a tiny warp bubble structure during analysis of Casimir cavities. They were modeling complex cavity geometries, shapes that might enhance the Casimir effect, and found that certain configurations produced space-time perturbations resembling a microscopic warp bubble. This generated significant media attention. Had we accidentally created a warp bubble? The answer is almost certainly no. What White and colleagues found was that the mathematical model, under certain idealized conditions, produced a space-time structure with some similarities to a warp bubble. But this was in a theoretical analysis, not an experimental observation. The structures were incredibly tiny, far below scales where they'd be useful, and it's not clear that the modeling accurately represents physical reality. Other physicists were skeptical, pointing out that the analysis made assumptions that might not hold in real Casimir cavities. Nevertheless, the work is part of a broader effort to understand whether quantum effects like the Casimir effect could be harnessed to produce warp-like spacetime geometries. Even if we can't create a macroscopic warp bubble, studying microscopic analogs could teach us about the fundamental physics involved. Another area of investigation is analog warp drives. These are systems in fluids, optical media, or other materials that mimic some properties of warp drive spacetimes. For instance, moving disturbances in certain fluids can create wave patterns that bear mathematical resemblance to warp bubbles. Light traveling through carefully engineered optical media can experience effective geometries similar to curved spacetime. These analogs can't produce actual faster-than-light travel, but they can be used to test certain predictions of warp drive physics in controlled laboratory settings. They're a way to explore the concepts when we can't build the real thing. Researchers have also been exploring whether warp drives could be detected if they exist. If an advanced alien civilization uses warp drives, would we be able to observe evidence of their use? Warp bubbles would create distinctive signatures in spacetime, gravitational wave bursts, or other detectable phenomena. Our gravitational wave detectors, like LIGO and Virgo, are becoming increasingly sensitive. While they're currently tuned to detect events like merging black holes and neutron stars, future detectors might be able to pick up other gravitational phenomena. If warp drives produce characteristic gravitational waves, we might detect them, providing evidence of advanced civilizations even if we never meet them. Of course, this assumes we'd recognize the signature for what it is. We'd need theoretical models predicting what warp drive gravitational waves look like, and we'd need to distinguish them from natural astrophysical sources. But it's an intriguing possibility that the search for extraterrestrial intelligence might not just involve radio signals, but also gravitational wave astronomy. What about the possibility that we're approaching this all wrong? That warp drives as currently conceived aren't the path to faster-than-light travel, but that some other, completely different approach might work? This is entirely possible. Our understanding of fundamental physics is incomplete. We know there's dark matter, making up about 27% of the universe's mass energy, but we don't know what it is. We know there's dark energy, driving the accelerating expansion of the universe, making up about 68% of mass energy, but we don't know what it is. The ordinary matter we understand makes up only about 5% of the universe. We don't have a working theory of quantum gravity. String theory, loop quantum gravity, and other candidates exist, but none are confirmed. We don't understand the fundamental nature of time, why it has an arrow, why we remember the past but not the future. We don't know if our universe is the only one or part of a vast multiverse. We don't know if the laws of physics are the same everywhere or if they vary in different cosmic domains. Given how much we don't know, it's entirely plausible that future discoveries will reveal new phenomena we can't currently imagine. Maybe some property of dark matter or dark energy can be harnessed for propulsion. Maybe quantum gravity will reveal shortcuts through space-time. Maybe consciousness or information has properties we don't understand that could be exploited. These are wild speculations, but the history of science is full of surprises. Consider what someone in 1900 would have thought about nuclear energy, lasers, transistors, the internet, genetic engineering, or quantum computers. All of these were completely unforeseeable because the underlying physics wasn't known. Someone in 1900 might have reasonably said that certain things were impossible based on the knowledge of the time, and they would have been wrong. Are we making the same mistake when we say warp drives are impractical or impossible? Maybe. But there's a difference between saying, we haven't discovered the physics that allows this yet, and this is prohibited by well-tested fundamental principles. Heavier-than-air flight wasn't prohibited by any physical principles. It just required engineering. Nuclear energy became possible once we understood nuclear physics. It wasn't prohibited, it was unknown. Warp drives aren't unknown. They're solutions to our best theory of gravity, general relativity. But they require conditions, exotic matter or vast energies, that we don't know how to achieve and that might be fundamentally impossible to achieve. Still, the honest answer is we don't know. And that means we should keep investigating, keep thinking about it, keep the possibility alive. The potential payoff is too great to dismiss out of hand. What would discovering that warp drives are definitively impossible do to us as a civilization? It would be a kind of bereavement, a mourning for a future we hoped for but will never have. We'd need to recalibrate our dreams. Perhaps we'd focus on other forms of exploration, virtual realities, inner space rather than outer space, extending lifespans so that slow interstellar journeys become bearable, digital uploads that could travel as information and be reconstituted at the destination, or sending robotic probes and experiencing distant worlds through telemetry. Alternatively, perhaps we'd double down on generation ships and cryogenic suspension. If the stars can only be reached slowly, so be it. Slow is better than never. We could still spread to the stars. It would just take a long time. Humanity could still become a multi-system, even multi-galactic species over millions of years. The timescales would be longer than we'd like, but geological and evolutionary timescales are long too, and life persists. On the other hand, what if warp drives are proven possible, and we develop them? This would arguably be the most important technological achievement in human history. It would fundamentally alter the trajectory of our species and our descendants. The coming centuries would see an explosion outward, the establishment of colonies on exoplanets, the discovery of alien life if it exists, the harnessing of galactic resources, and the diversification of humanity into forms adapted to different worlds and different purposes. But it would also bring challenges. The governance of an interstellar civilization, the potential for conflict, the ethical questions of terraforming worlds or encountering alien life, the existential risks of technologies powerful enough to warp spacetime. These would all need to be navigated with wisdom we might not possess. There's a concept in future studies called the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964. It classifies civilizations by their energy use. A Type 1 civilization can harness all the energy available on its home planet. A Type 2 civilization can harness the energy of its star, possibly by building a Dyson sphere. A Type 3 civilization can harness the energy of its entire galaxy. Humanity is currently at about Type 0.7. Not yet at Type 1. We can't harness all of Earth's energy. We use only a fraction. To reach Type 1, we'd need to fully utilize solar, geothermal, wind, tidal, and other energy sources on a global scale. To reach Type 2, we'd need to expand into the solar system and build megastructures. To reach Type 3, we'd need to spread across the galaxy. Crucially, reaching Type 3 almost certainly requires faster-than-light travel. Without it, the timescales are too long, the coordination too difficult. A galactic civilization at slower than light speeds would be more like a diaspora of disconnected cultures than a unified civilization. With FTL, a true Type 3 civilization becomes possible. Where would we be on that scale in the future? If we develop warp drives within the next few centuries, we might reach Type 2 within 1,000 years and Type 3 within tens of thousands of years. These are long time scales by human standards, but eye blinks in cosmic history. Without FTL, we might stagnate at Type 1 or low Type 2, confined to our solar system or a small bubble of nearby stars, never achieving our full potential. Do you ever think about your place in this vast cosmic story? About whether humanity will reach the stars, and if so, whether your life, your choices, the work you do today, contributes to that future in any way? It's easy to feel insignificant, to think that such grand futures, if they happen at all, will be so distant that they have no connection to us. But every great journey begins with small steps. Every achievement builds on the accumulated work of generations. The physicists working on warp drive theory today are building on Einstein's work from over a century ago. Future engineers who might build warp drives will build on the work being done now. And it's not just scientists and engineers. The artists, writers, and filmmakers who keep the dream alive in popular culture, who inspire young people to pursue science and exploration, they contribute too. The educators teaching physics and mathematics, the politicians and voters who decide whether to fund scientific research, the entrepreneurs building space companies, even the ordinary people who look up at the night sky and wonder, all of us are part of the story. Let's consider some of the specific technological challenges that would need to be overcome, assuming the fundamental physics allows for warp drives. First, you need a power source. Even in the most optimistic energy estimates, we're talking about generating power on scales far beyond anything we currently have. Our most powerful energy sources are nuclear, either fission or fusion. Fission is mature technology, but it has limited energy density. Fusion is still experimental, but if we can make it work efficiently, it offers much higher energy density. Beyond fusion is antimatter annihilation, which converts matter entirely into energy with 100% efficiency according to E equals mc squared. Antimatter is real. We create it in particle accelerators all the time, and we've even created and briefly stored anti-hydrogen atoms. But we create it in minuscule quantities, individual atoms or smaller particles. And storing it requires magnetic or electric field containment because if antimatter touches normal matter, they annihilate. The engineering challenges of producing, storing, and safely harnessing antimatter in the quantities needed for a warp drive are staggering. Beyond antimatter, you'd need to look at more exotic energy sources. Vacuum energy, the zero-point energy of quantum fields, theoretically pervades all of space. If we could tap into it, the energy would be effectively unlimited. But we don't know how to extract vacuum energy. The Casimir effect shows that vacuum energy is real, but extracting useful work from it is another matter entirely. Some proposals suggest using quantum field manipulation, but these are highly speculative. Then there's the matter of exotic matter itself. If you need negative energy density, where do you get it? The Casimir effect produces negative energy between parallel plates, but it's a tiny effect. Scaling it up might be impossible. Another quantum effect, called the dynamical Casimir effect, might generate negative energy through accelerating mirrors or boundaries in quantum fields. But again, this has only been demonstrated on microscopic scales. Some physicists have speculated about using traversable wormholes as a source of exotic matter. If wormholes exist or can be created, they require exotic matter to remain open, which means they might contain or be made of the stuff you need. Of course, this creates a circular problem. You need exotic matter to make a wormhole, and you need a wormhole to get exotic matter. Unless you find a naturally occurring wormhole, but we've never detected one, and there's no confirmed mechanism for their natural formation. Another approach is to look at quantum field effects in curved spacetime. Physicist Stephen Hawking showed that black holes should emit radiation due to quantum effects near the event horizon, now called Hawking radiation. This radiation represents a flow of negative energy into the black hole and positive energy outward. If you could harness the quantum field effects around black holes or other extreme space-time curvatures, you might generate the negative energy needed for warp drives. But operating near black holes is hazardous, to say the least, and this assumes you can control and direct the negative energy, which we don't know how to do. There's also the concept of chronology protection. Physicist Stephen Hawking proposed the chronology protection conjecture, which states that the laws of physics prevent the formation of closed time-like curves, paths through space-time that loop back on themselves, allowing time travel. Warp drives, if they allow faster-than-light travel, might enable time travel paradoxes. Hawking's conjecture suggests that quantum effects would prevent this, possibly by making warp bubbles unstable or impossible to form whenever they would allow paradoxes. This conjecture has never been proven, but it reflects a belief among many physicists that the universe must have safeguards against causality violations. If true, it might mean that warp drives are impossible for fundamental reasons we haven't fully understood yet. Or it might mean that warp drives are possible but can't be used in ways that create paradoxes. The implications are unclear. Assuming you overcome all these obstacles and build a working warp drive, there are operational challenges. How do you test it safely? You can't exactly take a prototype faster-than-light ship on a test flight without extensive prior testing. But how do you test something that operates in regimes we've never accessed? It's like trying to test an airplane before understanding aerodynamics. The first attempts would be extremely dangerous. You'd probably start with unmanned probes, sending them on short FTL hops and trying to recover them to see if they survived intact. But if something goes wrong, if the warp bubble becomes unstable, what happens to the probe? Does it get destroyed? Thrown into a different location in space or time? Turned into radiation? Without theoretical understanding backed by experiments, you're flying blind. And then there's the human factor. If you're inside a warp bubble, what do you experience? Is there radiation exposure from the warped space-time itself? Are there psychological effects from being surrounded by such extreme geometry? What if the warp bubble fails while you're inside it? Do you get dropped back into normal space at high velocity, experiencing lethal acceleration? These are questions that would need answers before putting people into warp ships. Assuming you work out all the kinks, what would interstellar travel actually be like with a warp drive? Depending on the maximum speed, trips might take days to years. During that time, you're inside a bubble of normal space, isolated from the outside universe. It would likely be quiet, perhaps eerily so. No engine vibrations because you're not moving through space locally. The space is moving. You might not feel any acceleration at all. Looking out windows, if you have them, you'd see... what? Possibly nothing. Possibly a distorted view of stars, light bent and warped by the geometry surrounding you. The experience might be more like being in a sealed room than like travel as we understand it. And when you arrive, when the warp bubble collapses, you'd suddenly be in a new star system, light years from home. The isolation would be profound. Radio signals back to Earth would take years to arrive. If something went wrong, there'd be no help coming. This isolation raises interesting questions about the psychology of interstellar travelers. Even with warp drive, space is vast and empty and dangerous. The people who venture out to new stars would need to be resilient, adaptable, comfortable with isolation and risk. They'd be like the explorers of Earth's age of sail, venturing into unknown waters with no guarantee of return. Some would thrive on that adventure. Others would find it terrifying. And what about the destinations? Current exoplanet science tells us that planets are common. Most stars have them. Many are rocky worlds in the habitable zones of their stars where liquid water could exist. But habitable doesn't mean inhabited, and it doesn't even necessarily mean comfortable for humans. Atmosphere composition, gravity, radiation levels, the presence or absence of a magnetic field, the stability of the climate, All these factors determine whether a world is actually suitable for humans. We might find that truly Earth-like planets are rare. Most worlds would require extensive terraforming or the use of sealed habitats. Terraforming, the process of modifying a planet's environment to make it Earth-like, would take centuries or millennia with known techniques. It would involve altering the atmosphere, perhaps by releasing greenhouse gases to warm a cold planet or using photosynthetic organisms to generate oxygen. It would require melting ice caps or importing water if the planet is dry. It's a colossal undertaking, and there are ethical questions. If a planet has native life, even microbial life, do we have the right to terraform it, potentially wiping out that life? Or do we have an obligation to preserve it, study it, learn from it, even if that means we can't settle there? These questions don't have easy answers. Some futurists propose that humans might genetically modify ourselves to adapt to different worlds rather than modifying the worlds to suit us. Increased radiation resistance, different atmospheric requirements, varied gravity tolerances. These could be engineered into human biology. But that raises its own ethical questions and might lead to divergent human species, adapted to different worlds and no longer fully compatible with each other. The future of a warp-capable humanity might be stranger and more diverse than we imagine. Not a monolithic galactic empire, but a patchwork of human and post-human civilizations, each adapted to its own world, connected by warp-capable ships but increasingly divergent in biology, culture, and values. Over tens of thousands of years, the differences might become so great that communication and mutual understanding become difficult. We might seed the galaxy with life and intelligence, but that life might not remain recognizably human. Is that a good outcome or a troubling one? It depends on your values. If you value diversity, exploration, and the spread of life and intelligence, it's wonderful. If you value human unity and the preservation of our identity, it's concerning. Probably, it's both. Let's return once more to the Fermi paradox and its implications for warp drives. If warp drives are possible and not incomprehensibly difficult to build, why don't we see evidence of alien civilizations using them? The galaxy is billions of years old. Even if intelligent life is rare, it's had ample time to arise and spread. If even one species developed warp drives a million years ago, they could have colonized the entire galaxy by now. Where are they? One possibility is that we're the first. In a galaxy of hundreds of billions of stars, someone has to be first, and maybe it's us. This seems unlikely but not impossible. Another possibility is that intelligent life is so rare that the nearest civilization is thousands or millions of light years away, too far for us to detect their presence. Another is that civilizations don't last long enough to colonize the galaxy. They destroy themselves through war, environmental collapse, or other means before achieving widespread interstellar travel. Or perhaps there's something about the galaxy that makes colonization difficult or undesirable. Maybe habitable worlds are rarer than we think. Maybe there are dangers in interstellar space, radiation, rogue black holes, or other hazards that make travel perilous. Maybe advanced civilizations choose not to expand physically, preferring virtual realities or other forms of existence. Or, more darkly, perhaps there's a predator or a hazard that eliminates civilizations that become too visible. This is the dark forest hypothesis, popularized by the science fiction novel The Three-Body Problem by Liu Cixin. The idea is that the galaxy is filled with civilizations, but they all hide because revealing yourself invites destruction from others. In this scenario, using warp drives or other highly visible technologies would be dangerous. There's no evidence for the dark forest hypothesis, and it requires assuming that all civilizations are hostile and paranoid, which seems unlikely. But it's a scenario worth considering when thinking about the risks of interstellar exploration. Alternatively, maybe we are being watched. Maybe there are advanced civilizations out there that are aware of us but choose not to make contact, perhaps following a non-interference directive like Star Trek's Prime Directive. They might wait until we reach a certain level of technological or social development before revealing themselves. This is the zoo hypothesis, and it's unfalsifiable, which makes it unsatisfying scientifically, but it can't be ruled out. The truth is we don't know why the galaxy appears silent. The Fermi paradox remains one of the most profound mysteries in science. And it has implications for warp drives, because if warp drives are possible and practical, the paradox becomes even more puzzling. If they're not possible or are impractical, that might partly explain why the galaxy hasn't been colonized. As we approach the end of this exploration, let's consider where the research stands now and what the future might hold. Warp drive research exists in a niche space, pursued by a small number of physicists, often on the margins of mainstream academia. It's not a major field like particle physics or cosmology. Funding is limited. Most physicists focus on more immediate, testable questions. But the research continues, driven by curiosity and the tantalizing possibility that it might lead somewhere. In recent years, there's been a slight increase in institutional interest. DARPA's funding, NASA's past involvement through EagleWorks, and the publication of papers in peer-reviewed journals all suggest that the topic is gaining a bit more legitimacy. It's moving from purely speculative to exploratory. We're still far from engineering, but the theoretical foundations are being laid. The next steps in warp drive research likely involve better understanding of quantum field theory in curved spacetime, experimental tests of Casimir and related effects at larger scales, improved models of how matter and energy behave in extreme spacetime geometries, and possibly discoveries in quantum gravity that reveal new possibilities. None of this will happen quickly. We're talking about decades of work, perhaps longer. In the meantime, other areas of space technology are advancing. Reusable rockets are reducing the cost of access to space. Plans for moon bases and Mars missions are moving forward. Concepts for interplanetary travel are maturing. These nearer-term goals don't require warp drives, and they're valuable in their own right. Even if we never achieve faster-than-light travel, becoming a spacefaring species within our solar system is an achievement worth pursuing. But the dream of the stars remains. And as long as it remains even remotely possible that warp drives could work, people will pursue it. Because the alternative, accepting permanent confinement to a tiny region of space, is too bleak for many to contemplate. What's your intuition? Do you think faster-than-light travel will ever be achieved? Not just by some alien civilization somewhere in the universe, but by us, by humanity or our descendants. Do you think someone 1,000 years from now will look back at our current struggles to understand warp drives the way we look back at early attempts to understand flight? Or do you think the barriers are insurmountable, that the dream is impossible, and future generations will pursue other dreams instead? There's no right answer. The universe hasn't told us yet. The laws of physics remain partially hidden, their full implications not yet understood. We're like people in a dark room, feeling our way along the walls, trying to figure out the shape of the space we're in. Occasionally, we find a door, a new possibility. Warp drives might be one of those doors. Or they might be a picture of a door painted on a wall, tantalizing but impassable. The only way to find out is to keep exploring, keep questioning, keep pushing the boundaries of knowledge. That's what humans do. It's what we've always done. From the first person who looked at the horizon and wondered what was beyond it, to the astronomers who mapped distant galaxies, we are explorers. The medium changes, from physical terrain to intellectual frontiers, but the drive remains. Imagine a moment, centuries from now. A ship hangs in the darkness of space, far from any star. Inside, a crew makes final preparations. They've calculated the trajectory, charged the systems, said their farewells to the solar system. Now, they initiate the warp drive. Space itself begins to bend around the ship, contracting ahead, expanding behind. Slowly at first, then faster, the bubble of warped spacetime accelerates. Stars that were fixed points begin to shift, distort. The ship isn't moving, not through space, but space is moving, carrying the ship with it. Inside, the crew feels nothing unusual. Gravity is normal. Time passes normally. They could be sitting in a room on Earth for all the physical sensation tells them. But outside, the universe is being traversed at speeds that should be impossible. Light years pass in hours. The distance that would take conventional spacecraft millennia to cross slides by in a journey measured in days. And then, deceleration. The warp bubble collapses. Space snaps back to its normal geometry. The ship drifts in normal space again, but the stars have changed. Constellations are unrecognizable. The sun is an invisible point lost among millions of others. Ahead, a new star blazes, and around it orbit worlds never before seen by human eyes. The crew looks at each other. They've done it. They've traveled faster than light. They've reached another star. Humanity is no longer confined to one small corner of space. The galaxy is open. Will this moment ever come? Will humans ever stand in a ship in orbit around a distant world, knowing that Earth is light years away but reachable in days, not generations? Will we solve the puzzle of space-time manipulation, harness the exotic energies needed, and break free from the cosmic speed limit? Or will we remain forever Earthbound, or at best solar system bound, watching the stars with instruments but never touching them, dreaming dreams that reality cannot fulfill? The answer lies somewhere in the future, hidden in discoveries not yet made, in technologies not yet invented, in the choices of generations not yet born. The laws of physics will not change to suit our desires, but our understanding of those laws deepens with every passing year. What seems impossible today might be routine tomorrow, or it might remain impossible forever. Warp drive sits at this edge of possibility, a concept that tantalizes because it is not quite forbidden, not quite achievable, existing in the liminal space between fantasy and physics. It represents one of humanity's deepest aspirations, the desire to transcend our limitations and claim a place among the stars. Whether that desire will ever be fulfilled, we do not know. But the fact that we can even ask the question, that we can write the equations and contemplate the possibilities, that we have learned enough about the universe to imagine such things, that itself is extraordinary. A few centuries ago, we didn't know that other stars existed, let alone that they might be reachable. A few decades ago, we didn't know that planets orbited other stars. Now we know thousands of exoplanets exist, and we can seriously discuss the physics of traveling to them faster than light. The progression of knowledge is staggering when you step back and look at it, and it shows no signs of stopping. We will learn more. We will push further. We will ask deeper questions. And perhaps, just perhaps, the universe will reveal to us the secret of how to slip the bonds that currently hold us and step out into the wider cosmos. Until that day, if it ever comes, we wait. We research. We dream. We look up at the night sky and imagine what might be. And in that act of imagination, in the refusal to accept that the stars must forever remain out of reach, there is something profoundly human, something beautiful and defiant and hopeful. The universe is vast beyond comprehension. It is old beyond measure. It contains wonders we have barely begun to glimpse. And somewhere, in the mathematics that describes its deepest workings, there might be a pathway to the stars. The warp drive, whether it's the Alcubierre metric or some other configuration not yet imagined, might be that pathway. Or it might not. The universe does not owe us faster-than-light travel. It does not owe us anything. But it has surprised us before, revealing possibilities we never suspected. It might surprise us again. The story of warp drives is not yet finished. It's being written right now in research labs and theoretical papers, in computer simulations and thought experiments. You are living in the time when this story is unfolding. Future historians, if they exist and if warp drives become reality, will look back at this era as the beginning, the time when humanity first seriously grappled with the question of faster-than-light travel. Or, if warp drives never come to be, they might look back at this as a period of hopeful speculation, a dream that inspired but was never realized. Either way, it's a significant moment. You are part of it. So when you look up at the night sky, when you see those distant points of light and feel that pull, that longing to reach them, know that you're feeling something that has driven our species from the beginning. The desire to explore, to go beyond, to reach the unreachable. That desire has taken us from the savannas of Africa to the surface of the moon. Where it takes us next, only time will tell. But the journey continues. The questions remain. And as long as we keep asking, keep searching, keep dreaming, the possibility remains alive. The stars await. Whether we will ever reach them, we do not yet know. But we reach toward them nonetheless, because that is what we do. That is who we are. And that, perhaps, is the most important part of the story.